So I'm going to try to pull together some of the themes you heard about today to kind of wrap some things in slightly different ways and to add a little bit of nuance to a few things. Because of that effort to try to kind of come to some conclusions about the whole day, I've been changing my slides as I went along, so I have no idea what's on them now. So we'll just go for it. So who knows what's on them? All right. So the idea is that in a way, what you're asking of cognitive neuroscientists, to the extent that they're included here, is for applications, right? This is a translational application of neuroscience to law. For example, I'm a neurologist and a cognitive neuroscientist, so I know a bit about the idea of translating basic research to medicine, to clinical practice, and that's challenging. I think it gets even more interesting in a way to apply these things outside of a clinical spectrum. So let me just try to take you through quickly again a quick review of the brain systems that produce behavior, which you've heard about today. I'm just going to try to put it together really quickly to give you a sort of overall picture. And then we'll talk, as everyone else has talked about, goal-directed behaviors and self-regulation and social behaviors, these highly relevant behaviors in the brain. Instead of talking in very broad terms about sort of the struggle between frontal and limbic systems, I'm going to drag you with me on a slightly more nuanced view, just to build on that platform, just to help you understand why we have a bit of trouble in some senses applying the fundamental work people are doing in cognitive neuroscience to real life. Because you'll see there's quite a bit of complexity to do that, and I'm going to show you examples. And I'm going to engage you, inspired by BJ, I'm going to get you to work on that sort of thing. And then that comes to the question of how predictably do brain pathologies disrupt behaviors? That's an important question. And are there clear lines between pathological and range of normal behaviors? And then, relatedly, what is the ecological validity, the application of neuroscience research on these points right now and in principle? So that's pretty lofty for 15 or 20 minutes. Okay, so brain and behavior. So here we go, quick review. Only I'm sort of filling in some background, right? So if you think about your brain in the world, what is it capable of? You can run kind of through a range of complexity of behaviors. You have reflexes, like the pupil constricting when light is shined on it. And then you have basic drives like hunger and thirst that trigger standard, pretty complicated behavioral repertoires, but very stereotyped. And then you have the term habits, which doesn't mean so much chewing your fingernails, but more elaborate learned repertoires of behavior that are triggered by cues, and that's a very important concept in drug addiction. But of course in real life, a lot of what we do is triggered by cues. In a certain circumstance, we emit a similar behavior. And that system relies on the basal ganglia, as we heard about just now. Somewhat more broadly, you can think about environmentally driven behaviors. So when you're in the world, in theory, you can do anything, but in practice, your brain's only contemplating a few possibilities. And it's contemplating a lot of the things that are just around you. So you're sitting there at the table, and there's a bunch of cups on the table, and even if you're not explicitly pondering your next action, your brain's kind of mapped out some possibilities for you. There's a cup you can reach, it would know how to get there, which arm to use, to be careful not to knock over the cup next to it. Some of that's maybe sitting in your motor system there, ready to go, if you decide to let it go. And to add a bit of sophistication to that environmentally driven behavior, you have to add on top the knowledge that that's not your cup, right? That that's your neighbor's cup. And then that's not the motor system anymore, that's a bit more elaborate, right? That's probably prefrontal information, additional context that's going to modify what your environment is suggesting you might want to do. So that's this idea of environmentally driven behaviors. They're suggested by the environment, and you do them. And a lot of the times that's very useful, but sometimes it's the wrong thing to do, if it's your neighbor's cup, for example. And then you get to goal-directed behaviors that we've been talking about, and that we usually think of ourselves as primarily being goal-directed people. And that's sort of kind of true, but maybe not as much as you might like to think. That of course we are able to pursue goals, but a lot of our behaviors are not like that. And even when we are pursuing goals, sometimes it's a rather simple-minded goal of just navigating to something we know is there but can't quite see, as opposed to the real lofty goals like being a better person or contributing to our community or something like that, that really is an abstract and distant multi-step sort of goal. And then there's rules, which is relevant because well, what are laws if not rules? So the degree to which these behaviors are possible is defined, by society, not just by our motor system. And so when you're looking at your world, at the things you might do, things that your culture and your legal system and your mom have told you are possibilities might exist on your menu, and other things will just fall right off the menu and won't be considerations for behavior. So the more elaborate you get, the more brain you need to do it. And the reflex that I'm showing you up there over and over again, probably rather irritatingly, is that's the one situation where I can tell you every time what's going to happen. I shine light on that eye every time that people will constrict, and if it doesn't constrict, I could figure out why. I could be very sure about why every single time. Very confident. It's just a couple of neurons to do that, and I could figure it out. And if the people didn't constrict, I would think there was something definitely wrong and go looking for it. And neurologists do this. But as soon as you move past that into the rest of behavior, the relationships start to get a lot more complicated. It becomes much harder to know, because the behavior is not being done the way you thought, that there's necessarily something wrong in the brain, or there's something wrong in the brain predicts necessarily that the behavior won't occur. And that's our problem from the point of view of helping you out. So I don't actually use fancy functional neuroimaging. You don't have to follow with me along multiple complex technical paths to understand the kind of research I do. I study people who have brain damage. So this is the skull of the famous patient from the 1840s, Phineas Gage, who had a metal rod driven through his frontal lobe and survived to tell the tale, and has had much post-media splash going on for more than a century, which I guess he's not benefiting much at this point. But, I'm contractually obliged to mention him in every talk I give because of my interest in decision-making and orbital frontal cortex. So here's poor Phineas. So we've known for a long time, the reason we think that the frontal lobes are important in these kinds of behaviors that we've been talking about today is because people with frontal lobe damage have trouble with those behaviors. Not because of fMRI. It's only after the fact that additional methods, converging methods, have helped us become more nuanced about exactly what and why, the mechanisms underlying that. So we can have brain disorders that can affect any of these levels of behavioral control, and that can also affect them in combination. You could talk about adolescence as an example of that, where both drives and goal-directedness are struggling with each other in a way that's different than in adults, for example. You can also think of it in terms of brain disorders where, for example, drugs might affect both frontal lobes and basal ganglia habit systems in the wrong direction. It's good to remember that a lot of the time these systems of the brain are actually all working together. We're not constantly struggling. Often we're actually all the parts of the brain are actually going for the same goal. All right, the other thing that's worth knowing about the frontal lobes in particular is that there's a lot of additional information that we've gathered that controls our behavior. As I was mentioning, the fact that the cup is someone else's, social signals, how the guy is looking at you as you start to reach for his cup. All those bits of information are also being processed through the brain and can be disordered by brain disorders. As can the regulation of your internal context, like an emotional state. So to talk about the frontal lobes in particular, because they're quite relevant, because that's what I study. So frontal behaviors, as I mentioned, have been known about for a long time. And typically you get this list of what is a frontal behavior, that people can be impulsive or distractible, capricious, driven by the environment, perseverate, be inflexible, have trouble organizing themselves, especially to meet distant goals, and then also be socially inappropriate, context insensitive, have trouble appreciating the impact of their actions on others, and aggressive or emotionally labile. These are not necessarily only restricted to the frontal lobes, but they're particularly notable features of frontal lobe function because as long as the injury is far enough ahead of the main motor and sensory systems, it can be all that people show. That's what's so striking about frontal patients, is they're walking and talking, but they're having all these difficulties with complex behavior. Fine. So here's where I'm going to get slightly more nuanced, because that level of description isn't really that helpful. It doesn't really get to mechanisms that you can understand in the brain. And maybe you don't care about mechanisms in the brain, but I'm going to argue that it probably is useful to understand mechanisms in the brain because it can be helpful for diagnosis. It can be helpful for knowing whether or not the behavior that's under discussion actually could possibly relate to the frontal lobe problem people are talking about. And it could suggest treatment or appropriate response to certain behaviors. So the brain is roughly modular. It does work in network ways, but to a first approximation, we can think of it in modular terms. And when you have complex behaviors, you're calling on lots of different modules. It is partly redundant. That's one of the things about those different levels of control. And even within one of the levels of control, there's different contributions, and so it's quite resistant to failure in general. And my main way of thinking about this is that dysfunction in any particular system simply tilts the playing field. And this happens to us in normal life. You know, to varying degrees, the playing field tilts, right? If we're distracted, or if we're hungry, or if we're in a situation where we've been in many times before, certain behaviors are more likely than others. And that's only further the case when there's a brain disorder. And the way that cognitive neuroscientists tend to go after this is to take these complex behaviors and then try to boil them down to much simpler behaviors, and then try to relate those to the brain. And then the idea is eventually we would build them back up again. It's that dotted line of building back up again that is the big challenge, that is what you need to be able to translate the sorts of things people are working on now back and say, okay, because of these deep understandings of the brain, now I know I can predict that this person's behavior will be like this. We have had a lot more success with that with simpler motor and sensory processes. When it comes to executive functions, decision making, social processes, emotion regulation, it's much newer terrain. We're making lots of progress. I think we're getting somewhere, but it's harder. Okay, so here's where you get involved. So this is the advanced version of what BJ had you doing earlier. So we're going to use your frontal lobes. You're going to do what it asks you to do. You'll see a bunch of letters one at a time. You want to look for the letter. You ask yourself, is the letter I'm looking at now the same as the letter I saw 2 trials before? So for example, A, B, E, B. That B you saw 2 trials before. Every time you see one that you've seen 2 trials before, I want you to tap on the table. All right, well, not bad for, 10 to 4. So what I was asking you to do was you use working memory. You have to hold something in mind when it's no longer present in the environment. This is the classic frontal lobe function. And then you were having to maintain that information against distraction because additional letters kept coming. And then you're having to update it. So all those things are definitely relying heavily on the frontal lobes. So it's called an end-back task, for what it's worth. And I want to just use it as an illustration of the complexity of figuring out how the brain actually does something like that. That seems like a very simple, it's a very classic, widely used task that's really getting at updating and working memory very elegantly. So you could ask yourself, where in the brain is this happening? So the kind of research I do, I actually take patients who've had brain injury. I take lots of them. So in this case, there's about 40-odd people who had focal brain damage in the past from strokes or tumor resections or whatever, where I could draw a line around where their lesion was, somewhere in the frontal lobes, and I collect lots of them, and then this is just showing you, in aggregate, how much of the frontal lobes were affected across the whole group, sort of stacked up lesions one on top of the next, so you can see which parts of the brain are affected. So the more sort of greenish, the more people there were with damage to those areas. Anything that's blue or anything you can see colored, we had coverage there with enough people with damage to those areas to be able to ask, does damage to a specific area relate to impairments on the task? So this is a lesion study. I didn't make the lesions. The patients suffer these events. I just give them the opportunity to contribute to science afterwards. So this is a method, a statistical method that actually goes in and says, comparing an individual person with the damage to this voxel in the brain against all the other people in our study, statistically speaking, where in that big mess of damage predicts difficulty with this task, this working memory task. And we found 2 areas, even though we were covering the whole frontal lobe, only 2 areas. This area here in the left lateral frontal lobe, which is what we were expecting to find. If you have damage there, you're impaired on this task. Overall, you perform poorly. The other place that is critical for this task is this anterior cingulate region that you've seen show up a lot. In some ways, this is a bit surprising, to me anyway. I didn't think it did anything, but it turns out it does something. So these 2 regions and nowhere else. So these people with frontal damage that spared these 2 regions don't have any problem with that rather hard task you just tried. But these two regions are not, they're working together, but they're not doing the same thing. One of them is contributing to that manipulation and working memory thing that we thought we were testing with this task. And the other one, this area here, is setting the response threshold. It's deciding how likely you are to produce that tap when you're in a situation of uncertainty, whether you're going to make a false alarm, as it's called. So normal subjects, and most of you, did not make any false alarms. I think someone did. I heard one. I'm sorry. That's true in this task. Normal subjects don't make false alarms very often, but people with this medial damage here, they made false alarms like crazy. It wasn't that they couldn't remember. They actually were okay at finding all the targets. They were just responding when they shouldn't to false alarms. So they were having a problem with response threshold. So even in this really simple task, there's two components of behavior you could pull out, and they're related to two different specific regions in the frontal lobes. Fine. So we've done that kind of work and covered the whole frontal lobe. I'm not going to take you through the whole business, except to just say, broadly speaking, you could say, okay, when we get experimental tasks that boil down to very specific behaviors, we can show that different regions of the frontal lobes are critical for certain aspects of working memory, visual, verbal, and the ventral frontal lobe, the orbital frontal cortex, important for feedback, learning, for recognizing emotions in others, and then this response control that you were just experiencing yourself. So giving you this information, now I'm going to ask you to put on your diagnostician's hats and say, okay, here's the frontal lobe, sort of explained. And then here's this patient who was in your briefing book, I'm sure you all studiously reviewed in detail, is this patient Mr. Oft, just to review for those who may forget. This is a case of a man who was developing in middle age interest in child pornography, went on to make some inappropriate advances to his stepdaughter, and ended up incarcerated for pedophilia, and then eventually was discovered to have this brain tumor, which was removed, and with this removal, his change in personality, his change in sex drive, and his sexual interest in children disappeared, and he returned to his family only to have this recur again, and it was found the tumor had regrown. And it was again treated, and he again did better. So here's a man with a very large tumor and cyst involving the frontal lobe here. If we can't agree about the contributions of this to his behavior, then we're going to have a lot of trouble thinking about the implications of much milder versions of brain dysfunction in the law. So I thought we should start by thinking about what about this. One question is, okay, he has this nasty-looking business here in his frontal lobe. If you only knew about this, could you conclude anything about its potential explanation for his behavior? And the answer to that is maybe not. The thing that's so compelling about his history is that it links very well in time to what occurred, and then he improves and the tumor is treated, and then when it recurs. So there's a lot of causality there, more than usual in neurological cases. But what's the cause of his aberrant behavior? Can we break it down to one of these frontal contributions? Was he having trouble responding to the feedback from his family that he shouldn't be acting that way, or recognizing that he might be doing harm to others? Was he having trouble just restraining his responses around interesting material? It's hard to say, right? Or was it all of the above? Well, with a tumor this big, you wouldn't be surprised if it was all of the above. And that's usually what happens. You're much more likely to see these major disordered behaviors from brain injury when the tumors are, or the brain dysfunction is large and extensive. That's when you see very compelling examples. So pathology-function relationships, there's a few rules of thumb. One is that large or bilateral or diffuse lesions have much greater impact on function. I study lots and lots of frontal patients. I don't know if I've ever met anyone who's interacted with the criminal justice system. So partly it's because I'm studying patients with focal lesions, restricted damage, and they're able to compensate for it in other ways. I can show they have trouble if I give them the right tests, but in real life, it may not be that obvious. So extensive traumatic brain injury, developmental delay, dementia, all of the above all at once, those are the patients who really show themselves to be frontal. It's because they're disconnecting massive amounts of their brain. For sure there's different effects if the damage is acquired in childhood than in adulthood, in good ways and bad ways. We can predict that a given lesion, I could have predicted that Mr. Oft might easily have personality change if you showed me his scan, but I couldn't be specific about it. I certainly would never have predicted specifically that he developed pedophilia. And in fact, I think is the only case reported anyway. It's not at all a direct one-to-one determination. Oh, there's damage there. For sure this person's going to have trouble with this. There's general rules of thumb. They're more or less reliable. Things get much more uncertain when you're dealing with more complex behavior. And then there's this problem of ecological validity. So even if I use my laboratory tasks, I could find out if this brain damage is causing trouble on specific component processes of executive function. I could tell you. But I wouldn't know for sure that that was playing out in real life, because that research has not really been well done, and it's difficult to do well. And to the extent that we've tried to do it, it's been largely inconclusive. You need very large samples because the complexity is so great. The other problem in general for thinking about frontal lobe function is that the normal range is broad. So we saw the spots on the graph that Vijay showed earlier, that there's wide ranges in adolescents but also in adults. So how do you know that the person with the tumor and the strange personality didn't just have a strange personality? I mean, there's all kinds of personalities out there, and the tumor is irrelevant, not the cause in any sense. And knowing that one way or the other, I don't know what difference it makes. The alternate point, though, that I wanted to make is that normal variations in behavioral tendencies, like impulsivity, for example, or variations in empathy or sociopathy, of course they're going to have a definable brain basis, not necessarily a tumor, but you're going to be able to see changes in the brain if you look. In some sense, the function of the brain must be different because they're functioning different than we might expect of the average person. It doesn't mean that the behaviors are determined or that the person can't be held responsible for them. All right, and this is the last kind of content point. So what counts as brain dysfunction? So visible neurological injury, Mr. Oft, I think it's quite likely that he has real brain dysfunction. We could probably agree on that. But then you get to neurological diagnoses that you can't necessarily see on a scan. Diffuse axonal injury and traumatic brain injury is not necessarily visible in imaging to go to pathology. And then you get to functional changes like the kind that Jeff Aguirre was talking about this morning. How far outside the normal range do they have to be, and how do we establish that? Those issues have already been raised. Cognitive test performance gets a lot closer to function, but we have the problem of knowing how to link that test performance to real life. What about psychiatric diagnoses? Psychiatric illnesses are also in the brain, and they do certainly affect, for example, frontal lobe or social functions, for reasons that we just don't understand yet, but they're still reasons. And then what do we do about variations with normal experience? So the multitasking brain, the fatigued brain, the stressed brain, the distracted or medicated brain. I can tell you already that there's going to be variations in frontal lobe functions, and to what extent is that an excuse for loss of control? I'm asking a bunch of questions, I'm not answering them. So I'm assuming you'll answer them in the question period. So the take-home points I wanted to make was that self-regulation, I think brain mechanistic approaches have more hope than others of coming to something that's truly explanatory, because we have the biology to kind of hold us. But they're still not to the point where you can apply them in a courtroom, I would say, in general. And that self-control can definitely be disabled in people with defined brain injury. I don't think there's any debate about that, in all kinds of ways. And we're, all kinds of ways that can be understood with more subtlety than just failure to overcome a strong drive. But there's some detail to how that goes wrong in an individual, depending on the individual cause and specific situation, that could be helpful to understand better, that could suggest the likelihood that that would be repeated, how much of it had to do with the specific situation they were in, or how could we potentially help or support people to avoid them doing that sort of thing again. In my own experience of seeing, of course you're seeing people who are charged with criminal behaviors who might have frontal lobe dysfunction, but I'm seeing people with frontal lobe dysfunction, very few of them are charged with criminal behaviors. But if you look at neurological, cognitively impaired people, neurologically, many of them are aggressive and violent even. But these are people with profound brain disorders. There's no sort of interesting subtlety to it. They're very, very unplugged with dementia, for example. And so it's a bit of a different story then. And the last point is that the reverse of inference is likely to hold, that otherwise healthy people who act in these ways will show abnormal brain function in the same circuits that, when injured, affect self-regulation. But this is an explanation, not excuse, basically. So I will stop there, and we'll see how much this links with the next talk. We'll see.